I know, right? Is a prime number.
A number can only be processed by multiplying one and itself.
Right. A prime number has two factors, one and itself. Now, when you give that definition, the problem with that definition is, of course, it has another word in it that needs a definition, right? Because if you don't know what a factor is, then that definition makes no sense to you. So, of course, what is a factor? Don't all rush to the answer. It's no, that's a prime number. You're back to prime number. That's a better definition of prime number since it doesn't use the word factor, and we need to know what a factor is.
Can I hear it in a sentence?
Huh? Yes, a prime number has two factors, one and itself. Two things. There you go. That's what a factor is. Any two, and there has to be two, any two numbers that multiply together are factors. 2 times 6, 12. 2 and 6 are the factors, 12 is the product, right? So, a prime number is any number with only two factors, one and itself. Now, to change that definition around slightly, as Hazel said, it means you can only divide that number by one and itself. Okay? Now, listen to me carefully, please. I cannot stress this enough. It is incredibly useful for you people to memorize all the prime numbers up to 30. It's really useful for future high-level math. What is the first one? No. 1 has one factor. 2. Why is 2 the most powerful prime number? Because it's the only even prime number. And then 3. What's next? 5, then 11, then 13, then 17, then 23, then 29. Know them, you're in good shape. Everybody cool? All right, that's the first part of today when we go back in the day. Everyone is good with that, yes? Now, prime numbers are actually pretty neat. You can do a crap ton of math with prime numbers. As a matter of fact, I firmly believe that, like the movie Contact, which none of you have seen because it came out in 1994, like the movie Contact, when aliens decide to communicate with us, they will use prime numbers because numbers are indeed a universal language. Everybody counts. You have to count. And it doesn't matter if you say this number right here is or 5. It's still this many things. Prime numbers are how I believe they will communicate with us. Of course, the message when we decipher it will be surrender or we'll destroy you, but that's okay too, because we deserve it. Really, Jess? You want to argue?
No.
Good.
I agree.
So, as I was saying before that, this is the first new thing we've done. Now, the neat thing about prime numbers is most of the time in math, there's patterns. For example, every perfect square, you add the next odd number to get to it. So 4, the next perfect square is 9. You would add 5. The next perfect square after 9 is 16. You add 7. The next perfect square after 16 is 25. You add 9. And it goes on and on and on forever and ever and ever. Like that weird chick in iCarly who lives in Olympia. But the girl who says you'll be in my basement forever and ever. Your loss, Anoop. It's a great bit of TV. I'm a huge iCarly fan. So, prime numbers, however, have absolutely no pattern, except that they're all, except for 2, odd. Now, the really neat thing about prime numbers, I think, is we keep discovering new ones. And the largest prime number, and I'm paraphrasing it best because I like math, it interests me, but I don't actually spend my spare time, learning esoteric math facts. But the largest prime number, if I'm not mistaken, is somewhere up in the billions, which is pretty wicked, I think, that you can have a number that big that has no other factors. Like, it's okay to say, 19, 1 in 19, big deal. But when it's 19,379,872,371, that's pretty damn cool, I think. You probably disagree. But that being said, if I invented some sort of candy-crushing app that's goal was prime numbers, all of you would be like, oh my God, it's the greatest thing ever. But I haven't, so we'll just talk about that. Everyone is good? Awesome. Now, as I said earlier, prime numbers are very powerful. They can be used to do a lot of other things. You're going to learn the first thing they are good for today. To do that, you need to go back again, cast your mind back to grade 6. For me, that means casting my mind back to leg warmers and oversized sweatshirts hanging off the shoulder. But for you, that isn't what that means. You're going to make a factor tree. You all made factor trees when you were little kids. You started with a big number. It was never as big as 54. It was a number like 20. But the method stays the same. And what you did was you thought of 2 numbers that were factors of 20. How did you know it was a factor? 20 could divide by those 2 numbers. So we are going to do the first one here with 54. What are 2 numbers that divide into 54? Levi. Right. We're going to start that one. Now, the factor tree is not done. That is but its first 2 branches. You continue factor trees until you end up with a prime number at the end of every branch. So what does 3 break down into? What does 9 break down into? 3 and 3. Are those prime numbers? Yes. So we stop anytime a branch goes to a prime number. What is 2 and 6? What is 6? You guys laugh at me, but it's hard to come up with all the knowledge and the material at the same time. Everyone is good? Now, of course, this means that 2 times 3 times 3 times 3 equals 54. And does it? Yes. 2 times 3 is 6. 3 times 3 is 9. 6 times 9 is 54. But we're in the 10th grade. Would we ever write this like this? No, because we're lazy like math people. How would we write this? 2 times Jesse.
2 times 3 to the third.
Thank you, Jesse. 2 times 3 to the third. Everybody good? Spectacular. Now, some of you will have been taught by your version of Mrs. Bad Crumble to make your factor trees sideways. That's cool too. I don't care. You can have a factor vine like strawberries, or you can have a factor tree like Christmas. You could do both. You could have the tree growing down like roots, and then you could have a vine like strawberries going out the side. I don't care, as long as you have all the prime numbers. Now, my grade 10 teacher said factor trees are for kindergartners, and he made us do a tree like this. And I'm only going to show you because I like this one too. That ends in 2, so you divide it by 2. 2 into 162 gets you 81. 81 divides by 3, that gets you 27. 27 divides by 3, that gets you 9, 3, 3. And you can see all my prime numbers are lined up nicely on the outside. I do not care what you do as long as you can find the prime factors of the number that I have asked you to work with. Okay? How it looks is up to you. So this would, of course, be 2 times 3 times 3 times 3 times 3 would equal 162, which is, of course, a dumb way to write it. 2 times 3 to the 4th would equal 162. Everybody remembers how to do this, yes? All of you drew factor trees in grade 5 or 6, right? Maybe even a little earlier, depending on how advanced your math teacher was back in the day. Now, the easiest thing that we can do with prime numbers is use them to find greatest common factors and lowest common multiples. I'm going to highlight these two terms because they come up all the time. Greatest common factor is GCF. You all know what a factor is. You all know what the word common means. You all know what the word greatest means. So what then is a greatest common factor? Times into, yes. Right. No, you're fine. The greatest common factor is indeed that. It is the largest factor of a group of numbers. Okay? Nice job. I can't hear that crinkling. I don't know you're about to eat in my class. You're very sneaky. You're almost like a ninja. Now, this is your first bit of possibly new knowledge. You may already know this. If you do, I apologize, but prime factorization is what we just did up there. You can use the prime factorization to find the greatest common factor by collecting the common factors from both, or I shouldn't say both, from all the factor trees. Now, GCFs are larger or smaller than the numbers you are working with. Smaller, because they are the things that build up, are less than or equal to the which? Smallest of your group or largest of your group? Right. GCFs are less than or equal to the smallest of the group. Now, why is that? Because, Hazel? Yes, exactly. Now, Hazel has already given us a way down here because she knows that the GCF of these two is 54, because 54 goes into 54 and it goes into 162. But that doesn't mean I'm still not going to show you how to do it. 54 is 2 times 3 cubed. Yes? And 162 is 2 times 3 to the 4th. Right? GCF, I'm highlighting it all in yellow. I must count only what is common. So for a GCF, I need the smallest exponent of the common factors. So, is 2 common to both of them? Yes. What is the smallest exponent there? 1. So my GCF must include a single 2. Is 3 common to both of them? Yes. What is the smallest exponent there? 3. So my GCF must include at least 3 3s, or at most 3 3s. So that is 54. And of course, as Hazel says, 54 is a factor of 54 because 1 times 54. And 54 is a factor of 162 because of 3 times 54. Is everybody good? Yeah? Is 54 less than or equal to my smallest number? Yes, because my smallest number was 54. Everyone is cool? Sweet. Nobody has trouble with that one. But a lot of people seem to have trouble with the lowest common multiple, which is LCM. Now, you're already used to doing lowest common multiple because it's what we do to add fractions, but we call it lowest common denominator. Most of you, however, cheat when you add fractions. For example, if I were to give you 4 and 6, a great many of you would cheat a little bit and say the lowest common denominator was 24. Because you've been taught if you can't figure it out, you can always just multiply the two together, right? It's obviously 12, but that is beside the point. So even though you are all capable and have used lowest common multiple all the time as lowest common denominator, we're going to do it another way here. The lowest common multiple is the smallest which has your entire group as factors. So your whole group has to be a factor of, your whole group has to have factors that both of your numbers are. And we remember that LCMs are greater than or equal to the largest of your group. And an LCM can be found by collecting all the factors. Please notice GCF was what? Common factors. LCM is all the factors, but we only count them once. So, come down to here. We got 54. We got 162. 2 times 3 cubed. 2 times 3 to the 4th. And for an LCM, we count all, but we only use the largest exponent in repeats. And this is our LCM. So, is there a 2 in both? Okay, I have to count 2's because I have to count everything. I use the largest exponent. What's the largest exponent with 2's? 1. So I count one single 2. Is 3 in both? Yes. So I count all the factors, but since I only count them once, so I use the largest exponent here, which is 3 to the 4th, which gives me 162, which I already knew from our GCF. Because 162 times 1, 162 multiplied by 1 is 162. 54 multiplied by 3 is 162. So 162 is the lowest common multiple of both of those numbers. Is everybody good? All right. Now, unlike grade 3, grade 4, grade 5, you are going to be using these factor trees tomorrow to do stuff. Okay? But today, we're going to practice factoring in general. Turn the page over. And there is our first set. 36 and 120. Make 2 factor trees, however you see fit. You like to go sideways, go sideways. You like to go up and down, go up and down. You like to make the staircase like I make, go ahead. But I want the factor trees, and then I want the list of factors written the way we would write them. Aight? Aight. Go. How many people's first branches were 6 and 6? How many people were 9 and 4? How many people were 12 and 3? How many people were 2 and 18? Nice. Okay. Now, you'll notice everybody's hands went up for different first branches, right? Does it matter? No, because do I care about the first branch? Do I care about any of the branches? No, I care about the circle at the end of the branch. When do you write that circle? When your branch hits a prime number. 2, 3, 2, 3. So 36 is 2 squared times 3 squared. Yeah? I like how you stick your tongue out when you're writing that down and looking up at the same time. I do that too. When you're cutting with scissors, do you do it then too?
I don't know.
$120. I bet your first branch is 12 and 10. How many people? Yeah? How many people did 2 and 60? Lame. Just kidding. It doesn't matter. 3 and 4. 2 and 2. 2 and 5. Everybody agree? Easy peasy lemon squeezy, yeah? Yeah? Okay. My GCF. What do I count? Common only, and which exponent? The biggest or the smallest? Smallest, because we're looking for smaller numbers, right? What is 2 in both? Yep. What's the smallest exponent of 2 that's in both? 2. So 2 squared. Is 3 in both? What's the common exponent, the smallest one that's in both? 1. So my GCF is 2 squared times 3. What is 2 squared? What is 4 times 3? 12, and we're done. My LCM, I count everything how many times? Once. And if there's a group, biggest or smallest exponent? Biggest. What is 2 in both? So I got to count it. What's the biggest exponent? 2 cubed. Is 3 in both? What's the biggest exponent? 3 squared. Do I have to count everything? Yeah, so I got to count that 5. What is 2 cubed? 8. What is 3 squared? 9. 8 times 9 is 72. What's 72 times 5? 360. And that's my LCM. And that makes sense because it's 36 times 10 and it's 120 times 3. Gouda? When does this serve purposes in real life? Well, you already know it's how you add fractions. But it's also how you design things, right? If you got to have for example, the stars on the American flag. If you look at it, they're not even rows. There's a bunch of stars, and there's less stars, and then there's a bunch of stars, and then there's less stars, right? That is when this comes into play, design. If you need to fill up a space with an unsquare number, that's how they do it. Right? Right. All of you do 18 and 24. It's a race. Go. Cheater. Calculator to divide 18 and 24 in honors math 10. Oh, okay. Oh, I see. All right. Okay. All right. I'm agreeing with you. Okay. Everybody should be getting fairly comfortable, yes? Now, this is an honors class. Too easy. And 60. And 42. And 63. This one's going to need how many factor trees? 3. This one's going to need how many factor trees? 4. Does anything change? No. Go. All the people that went ahead have already done 45 and 75 and 35 and 84, so now they just have to add 60 to the list and 42 and 63 to the list. Bad seed.
Yes. Just did it on my calculator.
Are you a ninja too? We don't actually do that, in any martial art.
I know.
No, you don't.
Yeah, I wasn't.
Karate Kid, yes. Karate Kid is a good version of the martial arts. It's done a lot to help that ancient tradition move forward. I did a lot of taking off my jacket as I earned my black belt. That's the new stupid one where he's the Kung Fu Kid and it's set in China.
Jaden Spence. Hey.
What's the GCF? What's the only thing common to all three of them? 3 and 5. So it is 15. What's the LCM? Is 2, do I count 2? How many 2s? 2 of them. Do I count 3s? How many 3s? 2 of them. Do I count 5s? How many 5s? 2 of them. To get 4 times 9 is 36. 36 times 25 is 750. Plus 6 times 25 is 300. 1,050. No! 36 times 25. 36 times 25 is 750. And 6 times 25 is 150, so it's 900.
Is that okay? Sorry.
What's my GCF? 7. What's my LCM? Whew, it's a big one. 2 squared times 3 squared times 5 times 7. 2 squared is 4. 3 squared is 9. 36. 36 times 5 is what? 180. 180 times 7? 1,260. How do I get the GCF where? 7 isn't all of them. It's the only one that is. Everybody Gouda? Ease bees lemon squeezy, yeah? Now please remember, this is not elementary school. You are going to use this for the next 5, 6 classes. All right? It's not over now. In grade 6, when you learned factor trees, you did 1,000 of them, and it was over, and you moved on to the next thing. Okay. Now, before I go on, I quickly want to hear, because you will notice that number 6 on your homework does not have an explanation in the answers. I want to hear some of your explanations. You all know that 6A is rational because it says so in the answer. Why? Because it ends. Right? When you write it out by hand, it ends. 1 root of 150 is not rational. Why? Why does it end on the calculator? Because your calculator runs out of space. Okay? That is important. 15, A, B, and C also didn't have an answer. Can somebody give me their answer to 15A? Pardon me? 3/4. Absolutely correct. Or any other fraction or decimal. A whole number, but not a natural number. 0, that's the only one. Any irrational number. Pi, square root of anything that isn't perfect. All right, good. Everyone was able to do this with a calculator? Yes? Remember, you must bracket the top to do so. Or you must do numerator equals divided by 2 equals. Right? Okay, we're good. Your work today, and you have half an hour to do it, is the left side of page 119. Only this side today. Okay? Now, listen to me for 1 sec. One of these pages has the wrong answers. Oh no, this page I fixed. Never mind. Page 140 on the left, that's what you're doing today. Gouda? Great.